Welcome back to Polymeric Biomaterials. We are looking at temperature and solvent effects, and in today's lecture we are continuing our discussion on solution thermodynamics. But today we are going to be looking at the Flory-Huggins theory for polymeric solutions. Now in this lecture we will firstly be looking at the physical framework of the Flory-Huggins theory, comparing and contrasting it with the ideal solution of small molecules that we saw in lecture 15. Then we will describe the Flory-Huggins lattice model, and as we did before for ideal solutions in lecture 15, we will look at the entropic and enthalpic contributions, and then finally determine the free energy of mixing based on the Flory-Huggins equation. And we will finally look at the Flory parameter as well as a means to understand polymer-solvent interactions. Now notice that in this lecture we are only looking at an overview of the Flory-Huggins theory for two reasons. One is we have dealt with the framework for solution thermodynamics in the earlier lecture, lecture 15. So if this is the first time you are looking at Flory-Huggins theory before you have looked at lecture 15, it would be good if you can go back and look at lecture 15 first, revise the concepts therein, and then come to this lecture. More importantly, we are also not going to derive all the steps of the Flory-Huggins theory. We are going to focus more on the concepts that relate to the physics of the problem, and we will largely be skipping the mathematical derivation, which is also important, perhaps in a different context. But in this course, since our goal is ultimately to be able to understand all of this in the context of polymeric biomaterials, we will not be focusing on that aspect of the Flory-Huggins theory. So we will first begin by comparing and contrasting ideal solutions that we saw in lecture 15 and polymer solutions. Recall that the delta H mix, delta V mix and delta S mix for ideal solutions that we saw in lecture 15, delta H mix and delta V mix are 0, delta S mix for the ideal mixing is a positive quantity. Overall, that makes delta G mix a negative quantity, which means mixing is always favored for ideal solutions, because the change in Gibbs free energy favors mixing spontaneously. Also recall that we saw the lattice model for small molecules back in lecture 15, where we have said that the total number of lattice sites is given by n sub naught, total number of solvent molecules is given as n1, and total number of solute molecules is given as n2. And just to point it out, although it might be quite obvious to you, for the ideal solution case of small molecules, the number of lattice sites occupied by a single solute molecule is 1, and the number of lattice sites occupied by a single solvent molecule is also 1. So if you consider this checkerboard here, as an example for a lattice, each solute molecule can occupy one spot only. Likewise, each solvent molecule can also occupy only one site. So there is a direct one-to-one correspondence between the number of solute molecules and the lattice sites that they occupy and the number of solvent molecules and the lattice sites that they occupy. This is a very important point to note here, because as we will see very shortly, but the case of the polymer, that will not be the same. So we will look at that when we come to that. So put a pin on this idea, because we will revisit this very shortly on a different slide in this lecture. And again, let me reiterate that if you are looking at this lecture without having looked at lecture 15, it might not help you very much. So it will be good if you can look through lecture 15, where we have laid the foundations for the concept that we will cover in this lecture. Now you take the case of polymers and polymer solutions. Polymer solutions deviate from ideality, the ideal mixing that we saw, largely due to two reasons. One is the large size of the macromolecules. So there is a very large difference in the size between the solvent molecule, for example, and the polymer molecule, which is the macromolecule. By definition, it is a very large molecule. The second thing that we saw there was delta HM or delta H mix was 0 for the ideal case, where the interactions between 1, 1, 2, 2 are considered to be the same as interactions between 1 and 2, namely solute and solvent. That will not be true here, where the molecular interactions with solvent may be favorable or unfavorable depending on the system. So, a polymer-polymer and a solvent-solvent interaction will not be the same as a polymer-solvent interaction. That is one of the ideas behind understanding polymer solutions as opposed to ideal solutions. Now, these two directly lead to two important considerations by Flory and Huggins for the development of their theory. One is the large size of the polymer molecules and the fact that they are interconnected means that the delta S mix will be different from the ideal case of small molecules. We will still be looking at the number of arrangements possible, but because now the polymer chains are very long and the fact that they are connected will now mean that the entropy that we will talk about will not be the same as the entropy that we saw in the case of small molecules. In fact, even in the pure state, we would have said for the case of small molecules, the pure state solute, the entropy is 0 because there is only one way to arrange. We will see here that even in the case of pure polymer, there can be many ways in which you can arrange the chains because the chains are all interconnected. So, that is one important point to note. The other important point is there are intermolecular interactions that could exist between the polymer and solvent which could be favorable or unfavorable depending upon the polymer solvent system. That means delta H mix is not equal to 0 for polymer solutions because 1, 2 interactions are not the same as 1, 1 and 2, 2 interactions. So, these 2 points will form the basis for how we will formulate Flory-Huggins starting off from the theory for ideal solutions. Now, we will look at the formulation for the Flory-Huggins lattice model, and that is given by the following ideas. Firstly, we assume that the polymer chain is connected through M mers, and each polymer chain has the same number of mers. This is a model, so remember we will have to make some assumptions. So, this is assumption 1, this is assumption 2, and can you recall what word we used in one of the earlier lectures when we said if all the polymer chains are of the same length, what kind of a system would that be called? If your understanding of molar mass is good, then you would immediately be able to answer that such a system is called a monodispersed system, where all the chains are the same length and the dispersity is exactly 1. In reality, this will never happen, but again this is a very good starting point for us to understand the Flory-Huggins model which assumes this. Also notice that as compared to small molecules, polymer molecules take up volume and they are long chains. So, you can't place somehow try to compress it and place a polymer chain onto a lattice site. You are working with a lattice model, you place the solute molecule onto the lattice site 1 to 1 just as you place the solvent molecule in the ideal case. But in the polymer case, while you can do that for the solvent, in the solute here which is a polymer, it is a long chain. Now, one thing we have to do is to understand how are we going to place this long chain onto the lattice site. So, one thing is very clear, you cannot place the entire chain onto one lattice site because of the size differences. So, one way we get around this problem, or Flory and Huggins get around this problem, is to assume that the mer or the segment size that you are talking about is comparable to the lattice site size, which is in turn comparable to the solvent size. So, while the chain itself may be very big, if you zoom in and look at only a mer, the length scale of that, the size of that will be of the same order of magnitude as perhaps a solvent molecule, and now you can come up with a one-to-one correspondence between solvent molecule in lattice site and mer and a lattice site, not chain. And if you have n0 lattice sites, each of those lattice sites can be occupied either by a mer or a solvent, and remember the mers will be connected in a polymer, and that is another constraint that Flory-Huggins will consider. The other assumption that we are making here is that of the mean field assumption, where you have an empty lattice to begin with and you start adding the polymer molecules. With further addition, what you are assuming is the existing molecules are uniformly distributed, or in other words, local interactions are determined solely by the average bulk composition, which means we are ignoring localized differences and individual fluctuations in this theory. We are considering that local interactions are solely determined by the average bulk composition, that is what is called the mean field theory. And the other, so this is the third assumption. The other point to think about is as the lattice sites get filled up, each site has fewer nearest vacancies, and this becomes important as we will show you pictorially very shortly. Because the chains are connected, you can't arbitrarily place the mer from a single chain onto lattice sites that are very far apart. If you place a mer on a certain lattice site, for example, here, you can't place the next mer here because the mers are connected. So, once you place the first mer, where the next mer can be placed will be only in the vicinity or what we call the neighboring sites. And as we fill more and more lattice sites, each site will have fewer nearest vacancies because other sites have gotten filled up. And remember, once you have filled up a site, you can't fill it up again. And once polymers are added, you add the solvent. And the fourth assumption is Flory-Huggins assumes that there is no volume change upon mixing. This is also not a great assumption to make, but it turns out that Flory-Huggins still is a very useful theory for us to understand polymer solutions. Now also would be a good time for you to pause and reflect on this idea, where here we said each chain is connected through m mers. Can you try and relate how m, number of mers here, is related to the degree of polymerization that we have seen earlier? So maybe you can think about that to get a better sense of what we are talking about in terms of m here. Now, for the Flory-Huggins theory, we consider N1 total number of solvent molecules. This remains exactly the same as the case of the ideal case of mixing, where N1 also happens to be the number of sites occupied by the solvent molecules. Because solvent molecules are small and the size is comparable to the lattice site, each solvent molecule can occupy one lattice site. That means there is a direct one-to-one correspondence between the number of solvent molecules and the number of sites occupied by the solvent molecules. So far, so good. We have not seen anything different from what we have seen for the ideal case of mixing of small molecules. Where the difference will come is for the solute. Namely, here you have N2 total number of polymer molecules, but remember that I can't fit N2 polymer molecules onto N2 lattice sites because of the size. So now I can only fit one mer per lattice site, which means the number of sites that are occupied by the polymer molecules will be m times N2, where m is a number of where m is the mers, right, per chain, and across chains you assume that number remains the same. And if you have N2 such polymer chains, polymer molecules, then you have m times N2 number of lattice sites to fill for the entire system. So I hope that difference is clear. And as you can easily see, m can be thought of as a ratio between the molar volume of the polymer to molar volume of the solvent. So therefore, the total number of lattice sites here, N0, will be N1 plus Mn2, whereas in the ideal case mixing of small molecules, we would have seen that it's simply N0 is given by N1 plus N2, where there is a one-to-one correspondence between number of solute molecules in lattice sites, number of solvent molecules in lattice sites. In the case of the polymer, while that is true for the solvent molecules, for the polymer molecules themselves that is not true. So, the number of lattice sites here will be higher because of the large number of because of the size of the macromolecule essentially. So, this table again here shows that for the solvent, the number of lattice sites occupied per molecule still remains 1, whereas the number of lattice sites occupied per molecule for the polymer will now be m. This is the polymer. I hope that difference is clear. This is a very important point to keep in mind. It turns out that this will make a very big difference to the final result we get. The form of the result interestingly will not look very different from what we have seen earlier, but how we are using or what variable we are using to understand polymer concentration in solution will no longer be mole fraction, but will be volume fraction, and that is because for polymers those are not the same. For small molecules they are the same. For polymers we are now switching to volume fractions, Phs, one because of the size, and two, for us to know mole fractions for polymers you have to know the exact molar mass and molar mass distributions, whereas volume fraction can be easily obtained if you have mass and density. So, it makes our life easier to deal with volume fractions for polymers rather than mole fractions, and volume fraction Phi1 for the solvent is given by N1 plus N1 over N1 plus Mn2, and volume fraction for the polymer Phi2 is given by Mn2 over N1 plus Mn2. You can very easily see that when m is equal to 1, you get back the ideal solution case, where you will simply have N1 over N1 plus N2 in both cases, if m is equal to 1, which is clearly not the case here. So, two things to take away from this slide. One is apart from the framework of the Flory-Huggins itself, one is that we have to account for the number of lattice sites occupied by the polymer molecules, and we are switching our nomenclature to volume fractions instead of mole fractions for polymers. Now, we will do the same thing that we did with ideal solutions. We are now going to look at entropic and enthalpic contributions to free energy of mixing, and we are going to compare the before state or the pure state, unmixed state, and the mixed polymer solvent state, and we are going to ask what is the change in enthalpy, what is the change in entropy. But before we do that, we will again look at the lattice model pictorially and try to understand how to think of arrangements both in the pure state and the mixed state. So, if you think of microstates and you hear the word microstates now, you should be able to relate it to the Boltzmann equation for entropy, where this has to do with the number of distinguishable unique arrangements that exist for a given macro state of the system. So, before mixing, for small molecules we saw that there was only one way to arrange them, right. If you replace a black with a black ball, we saw this in lecture 15, you will not be able to tell the difference. If you replace a red with a red ball, you will not be able to tell the difference, again assuming both are unmixed in the pure state. So, there is only one unique way for us to arrange, which means omega is 1, S will go to 0. Now, that is true for the solvent case here, because if I replace a black with a black ball here, you can't tell the difference. So, it is not a distinguishable arrangement, and I can make that same argument for all the black balls, which means there is only one unique way for me to arrange these 9 black balls as shown here. There is no difference between this and any other arrangement of black balls I can come up with for this system. So, that idea of one unique arrangement with S being 0 will hold true for the solvent case in the pure state. So, that is still true. Now, what about the polymer case? Unlike small molecules, polymer chains are connected as shown here. So, we are taking the example just as a test case of 2 chains of 8 mers each, or what we call 8 balls here connected by these yellow lines, indicating that this entire set of balls connected by the yellow line is one chain of the polymer. And remember, because Flory-Huggins assumes all the chains have the same length, m is same for all the N2 molecules. We consider a second chain also with 8 balls, but that is placed in a slightly different arrangement. Now you notice, because the chains are connected and because I can now arrange them in different ways, S is not going to be equal to 0 for this case, even in the pure state. In fact, you will have many distinguishable ways to arrange the polymers in the pure state. So, if I now take this arrangement and I arrange the if I arrange the polymer this way, I'll maybe show the connections in a different color so that you can appreciate the differences. Clearly you see these two are not the same. So, even in the pure state, what is important to appreciate is that the polymer will have many different arrangements that are possible, many different microstates that it can take in the pure state as compared to the small molecule solute. That is an important distinction to keep in mind. So, as a result, S2 here, that is the entropy of the pure state for the polymer, is not going to be 0. Now, what is the scenario in the mixed state? So, this is simply S1. What is the scenario in the mixed state? Polymer chains, remember in the Flory-Huggins model, we take an empty lattice and start adding all the polymer chains, and the polymer chains can take up different arrangements. Let us say I take the same matrix and I start adding the first mer here. Like I said earlier, I can't add the second mer here. I am constrained by adding the second mer in one of these 3 sites because of the connections the polymer has to make. So, I can add it here, or I can add it here, or I can add it here. Let us say I add it here. Now, the next mer cannot be placed here, cannot be placed here. It can either be placed here, or it can be placed here, or it can be placed here. So, you see the number of choices for me starts to go down as I start placing more and more mers, because if there are fewer number of adjacent neighbors where I can place the connected mers for a given chain. And what you will also see is that even in this arrangement, I can have many different configurations, because at every step I have choices, and based on probabilities I can determine how many such arrangements are possible if I have n2 number of chains each with m mers. That is a simple calculation that you can do. And also add to it the fact that finally you will also have the solvent that is being added. So, you have a mixture of both red and black balls. Here what I am showing is just one possible arrangement in the mixed state, where this chain has taken up this arrangement, second chain has taken up this arrangement. But remember, this is only one arrangement of many arrangements I can have, and this is just for 2 chains. Now, if you have many chains and many more solvent molecules, which is typically the case here, especially if you want to use the Stirling approximation that we saw earlier in lecture 15, ends have to be very large. So, when you have such large chains and large number of solvent and polymer molecules, then your number of possibilities for combinations and arrangements significantly go up, right, in the mixed state. So, now if you look at the entropic contributions towards free energy of mixing, we recall that S is given by the Boltzmann equation, and delta S mix, which is the entropy change associated with mixing, is given by entropy after mixing in the mixed state minus the sum of entropies in the pure state for the solvent and the polymer. Now, right away you can note that this term is going to go to 0, because in the pure state all the black balls in the solvent can be arranged only in one unique way. I cannot have more distinguishable ways to arrange the black balls. But S2, which is the entropy of the polymer itself, is not going to be 0, because you can have a large number of connected segments leading to many distinguishable microstates. So, delta S mix is going to be k times logarithm of ln of omega 1 2 over omega 2, and accounting for the number of distinguishable microstates that exist for the polymer in the pure state and in the mixed state for the polymer and solvent system, the details of which we are going to skip because that is something that is not the focus of this lecture. You can show that delta S mix, you will ultimately end up with an expression that looks like this, where this is the Boltzmann constant, this is the number of solvent molecules, this is the number of solute molecules, and Mn2, as we saw, N1 plus Mn2 is the total number of sites that are there in the lattice. Now, if you recast it in terms of moles and volume fractions, what you end up getting is minus R times N1 ln of Phi1 plus N2 ln of Phi2. Now, it might surprise you right away that this looks very similar to the expression we got for ideal solution of small molecules, with the only difference that we are using volume fractions instead of mole fractions. But that one difference is very important because for polymers, volume fractions are very large even for dilute solutions, and you will get very large appreciable differences as compared to the use of mole fractions. So, that is a very important point to keep in mind. And as always, this term is going to go negative. This term is negative but can also approach 0 for very large polymeric chains when you have very large M essentially. See, overall what you will see is delta S mix will still be positive for polymer solvent mixing. Now, you come to the enthalpy contributions towards Gibbs free energy. Now, we never looked at this in the ideal case because we said delta H mix for ideal case is 0. So, for polymer solutions, what we are seeing is we are going to determine pairwise changes to attractive dispersion or van der Waals interactions going from a 1-1 or a 2-2 state, namely the solvent-solvent interactions and polymer-polymer interactions to a polymer-solvent interaction state. And that is pictorially represented as given here, where you are accounting for not just on the lattice, you are not just accounting for the interactions, you are also accounting for the nearest neighbors. So, for 1-1-2 contact, the delta H mix can be given by H12 minus half of H11 plus H22. The half appears because you have 2 of them versus one final 1-2 interaction. So, if you account for the differences in interactions between polymer-polymer, solvent-solvent versus polymer and solvent, you will end accounting for the fact that this is based on the nearest neighbors, where a polymer in the vicinity of a solvent versus the polymer in the vicinity of a polymer based on volume fraction, etc. What you will end up getting is an expression for delta H mix that looks like this. Again, we have not gone through all the individual steps for this derivation because our goal is not to get lost in those details. Those are important. We will not get lost in those details for this lecture. Our goal is to finally understand the form of the expression that results from for delta H mix for polymer solvent, where it is given by RT N1 times Phi2 times, we have introduced a new variable called chi12, which is called the Flory parameter. The Flory parameter subsumes the 2 factors I talked about, namely the exchange energy and number of neighbors. So, one way to think about Flory parameter is to ask is to think about it in terms of the exchange energy per molecule normalized by the thermal energy, or in other words, what fraction of kT or thermal energy is required to lift, let us say, one molecule of solute from its state and pure state, one molecule of solvent from its pure state, and interchange them. That is why it is called exchange energy. Also on the lattice you have to account for the number of neighbors that are there. So, the Flory parameter subsumes all of that and gives us this very nice expression for delta H of mixing. Now that we have expressions for delta H of mixing and delta S mixing, we can now put 2 and 2 together and come up with an expression for delta G of mixing, which is just delta H mix minus T delta S mix. And if you substitute the expressions for delta H and delta S mix, you will see that delta G mix eventually results in an expression that gives you RT times N1 log Phi1 plus N2 log Phi2 plus N1 Phi2 times Chi12, where this represents the entropic contribution, and because it is always negative, it is going to favor mixing. Notice that this and this will always be negative. So, the overall that part of the equation will be negative. So, that is going to favor mixing always, and this represents the contact dissimilarity enthalpy contribution. Dissimilarity, what we mean is the neighborhood of a molecule of polymer changing from its own self to that of the solvent surrounding it. That is what we mean by dissimilarity. This is usually positive and opposes mixing, but again it depends on the value and the sign of Chi12. We first note that for polymer solutions, because Phi2 is very large, delta S mix, although it is positive, is not going to be very large. So, while delta S mix is going to favor mixing, it will not favor mixing as much as it will favor mixing in the case of ideal solution of small molecules. And if we extend that to a mixture of not a polymer solvent, but a polymer-polymer blend, then because both Phi1 and Phi2 are both very large, delta H mix is only weakly positive. So, while the change in entropy is going to favor mixing, it is going to barely favor mixing. And before we look at the Flory parameter, we will simply note a few limitations of the Flory-Huggins theory. In fact, Flory himself admits these limitations in his work, and that is a very important aspect. Even though it is his own work, he is very honest about the limitations of the work, and that is another lesson that we can learn from these great men, which is to be objective and critical of all work, even your own work. De omnibus dubitandum, as the Latin phrase goes, the ability to doubt everything that is presented to you. So, one is not accounting for individual polymer compositions. That was not accounted for anywhere in this theory that we looked at so far. It has the requirement of a strict lattice system, which is a very idealized system. You will not have that kind of a system or an arrangement in real life. This is another major limitation. Flory-Huggins does not account for volume changes upon mixing. And the last one is, while the Chi parameter subsumes some of the factors that we saw earlier, it is assumed to be independent of composition, which is also an assumption which is also a limitation of the Flory-Huggins theory. If you want to know more about Flory-Huggins, especially the mathematical aspects of the derivation and more insights into Flory-Huggins, here are some suggested references that you can look at. In this lecture, we have only looked at those aspects that pertain to this course on polymeric biomaterials, focusing on those aspects that we will also later use when we discuss Flory-Renner theory and Merrill-Pepper's equation for hydrogel swelling. So, this equation we will revisit again in a later lecture when we look at biomedical hydrogels. And before we conclude, we will say we will look at a few remarks on the Flory parameter itself. It is a dimensionless quantity and it is temperature dependent. This can be determined experimentally, and I will just in a minute show you how. And if you want to think about it physically, it gives you some information about the measure of attractive or repulsive interactions between the polymer and solvent. And shown here is a plot describing how Flory parameter depends on temperature. Typically at higher temperatures, the Flory parameter decreases, and as Flory parameter decreases, the solvent polymer interactions become favorable and system tends to be more miscible, which means mixing is more easily favored, which may explain why many systems of polymer solvent systems solubilize better when they are heated. This is one way to think about it. One example of that is given here. Now, we have introduced one more parameter for looking at polymer solvent interactions, but earlier in this course, in previous lectures, we have looked at other kinds of parameters to quantify or to understand polymer solvent interactions. One of them we looked at was the solubility parameter given by Hildebrandt, and another, if you recall, was the second virial coefficient. So, in closing, we will just show the relationship between the Flory parameter and the Hildebrandt and the second virial coefficient. So, again we note for non-polar polymers, which is typically the case for Hildebrandt, because it cannot account for polar interactions. If you recall, the relationship between Flory and the Hildebrandt is given by this equation, and again, as always, one of the limitations is this is always going to be positive, and if mixing has to be favored, the Flory parameter has to be negative. How do we know that? Just inspecting the Flory-Huggins equation. So, if this is negative, then that is going to favor mixing. And the other relationship we are seeing is that of the second virial coefficient with Flory parameter. When we looked at membrane osmometry, we were looking at osmotic pressure measurements, pi over C versus C. We saw that you can get the second virial coefficient from the slope of that line, and we would have said that in a theta solvent, A2 goes to 0, and you see here that if chi12 is half, A2 will go to 0, and that is why here we have said chi12 has to be half for the system to be in a ideal chain or a theta condition. And as we have already said, chi12 has to be negative for mixing to be favored, or even if it is positive, mixing can be favored if entropic contributions significantly dominate. So, I hope that gives you a reasonable overview of not just solution thermodynamics, but also understanding the implications of those in the context of understanding polymer solvent interactions and solubility of polymer in a solvent to prepare polymer solutions.